we're going to be doing a recap on transcendental equations. So, transcendental equations, they are basically 4 methods of solving transcendental equations. So the first one being the bisection method, and this being the easiest of all. So how do we use the bisection method? Let's take a rerun back to where the equations of polynomials. If you draw the graph of a quadratic equation, you will notice that you have something like a curve, either being a minimum or a maximum curve. And the strength of bisection method comes from the solutions to our equation being at this point, where y is equal to 0. So if we have a curve like this, which means now we have a curve like this. So if we pick two intervals, let's say here and here, you will notice that the corresponding values of x, the corresponding values of x, the corresponding values of y here, and the corresponding values of y here, you will notice that there are different parts of the real number line, where here is positive, here is negative. So we'll just find a way to start shortening both of them, shortening the distance, since we know that the answer to the question is actually at the 0 point. So now, how do we go about bisection methods? Once you have an interval and they tell you that the answer is between that interval, you begin to add both of them and divide by 2, just like the normal bisection. Take for example, if you have an interval, let's say 0, 1, and you're told that the answer to your equation is between this interval, all you do is you add both of them. Once you add both of them, 0 plus 1, you divide it by 2, so you have something like 0.5. Then once you have 0.5, you will now test if 0.5 is positive or negative. If it's positive, depending on which of these guys is positive, let's say I have here to be my positive part, I have here to be my negative part. If it is positive, it means you've bisected that line, you have shifted it closer. So let's say, let me pick from here. Okay, this my diagram does not fit what I want to say, but let's just say from here, and I have here. Now, these are my 2 points. Now, after doing this, and I discover that, okay, this is negative, and here is positive. And I know that this guy is positive. It means I've shifted this point somewhere here, closer here. So I can do for this again, and I'll get to a point whereby I'll be getting something very close to each other, where it will be very, very close to my answer. Now, let's pick an example so I can explain better. Let's pick an equation. Okay, so let's pick an equation where our f of x equals to x cubed minus x minus 1. So now, this equation, the first thing is you have to know your interval. Now, how do we know our interval? You are going to test, try and error. So you test for when x is equal to 0 from elementary mathematics. You know that your f of x becomes 0 cubed minus 0 minus 1. Okay, f of 0. And f of 0 is what? Minus, negative. Now, you test again for x equals 1. The aim of my testing is to find two different signs. If here is negative, then the other must be positive. So I can have an interval there. Now, if I have f of 1, I have 1 cubed minus 1 minus 1. And that's 1 minus 1 minus 1. So I still have negative also. So, okay, let me try for 2. F of 2. Now, my f of 2 becomes 2 cubed minus 2 minus 1. And that's 8 minus 2 minus 1. So this becomes 8 minus 2. That is 6 minus 1. This is 5. So now I have an interval from 2 to 1. Or preferably, you might say, okay, preferably it's 2 to 1. You can say 2 to 0. But you know that the longer your interval, the farther your interval is, the more your iteration. So now if I pick my intervals from 2 to 1, or I can even test, let me test for that to be safe. Let me test for f of, okay, let me rub this off. So let me test for f of 1.5. So that will be 1.5 cubed minus 1.5 minus 1. So using so I have 27 over 8 minus 1.5 minus 1. So it's also positive, which is 7 over 8. So now I can pick two very close intervals, which are 1.5 and 1. Don't forget, 1 is negative, but this is positive. Negative, positive. So I just have to pick two very close points and bisect them. So let's go. Now, so step 1, or we can call it 1. Step 1. So you do, since you have your two intervals, the interval is between 1, 1.5. So there's definitely an answer to this question there. So we pick 1 plus 1.5 divide by 2. So you have 1 plus 1.5 divide by 2. That's 1.25. So then you test again. So 1.25. So f of 1.25. Now in bisection method, we don't really care about the answer to f of 1.25. We just want to know if it's positive or negative. So here it is negative. So if it's negative, the next step is going to be replacing the negative part of this interval, which is 1. So the next iteration will be something like 1.25 plus 1.5 divided by 2. So you have 1.25 plus 1.5 divided by 2. So you have 1.375. Now, you test again. 1.375. This f of 1.375 means wherever in our original equation you put 1.375 there and get an answer. So you don't need the answer, you just need to know whether it's positive or negative. So here it is positive. So you would replace this here and you do that over and over and over till you get an answer. So depending, and don't forget, the further your interval, the more iteration you are going to do. So let me just complete this. So I'll replace this. I would have 1.25 plus 1.375. Now take note, if you are doing your iteration, you have to be careful of the decimal places you have to leave your answer in. So if the answer is in, let's say our answer, they ask us to leave our answer in 2 decimal places, it's going to be easy. But if you are asked to leave your answer in, let's say, like 5 decimal places, then you have to do more iteration and you have to be careful when approximating. In fact, I would advise you should not even approximate at all. Just use your calculator. Now, so you have 1.3125. You check again. You just need to check whether it's positive or it is negative. So in this case, it is what? Negative. We'll continue again. We'll continue from here. So I'm replacing it with 1.25. So I have 1.3125 plus 1.375. So as I'm doing this, I notice that these two, they are converging. So the first decimal place is 3. So you would continue. You do 1.3125 plus 375. So you have 1.34375. So check. So 1.34375. It is positive. So you would replace again. So you have 1.3125 plus 1.34375 divided by 2. So I have 1.328125. So you check positive or negative. So positive. You replace again. So you have 1.3125 plus 1.328125 divided by 2. One point 32033125. So f of 1.32033125 is what? Negative. And don't forget, I'm deciding to get my answer in 2 decimal places. So I can see 32. It is converging already. So let me try it once again. So if I'm going to replace this one with this. So I have 1.32033125 plus 1.328125. So that is 1.32421875. So I'll stop here since I'm deciding to take my answer at 2 decimal places. So my answer is approximately okay, f of x cubed minus x minus 1. So my answer x is approximately 1.32 to 2 decimal place. So that is bisection method. So I'll move on to the next. I'll move on to Newton-Raphson. So I'm going to be brief. So let's go to Newton-Raphson. Okay, so Newton-Raphson's method, the scheme. So it goes by the formula x I plus 1 equals xi minus f of xi over f prime of xi, where f of xi is the polynomial you're looking for. So preferably, I will still use this question. So the question is f of x equals x cubed minus x minus 1. Now, so how do I go about this? So first thing, let's first look for a very beautiful scheme for this question, because each question will have their own scheme. So that we'll not keep getting f of x1, f of x2. So let's look for a scheme where we can just plug and play. So now xi plus 1 equals, now this becomes our x. Okay, this becomes, let's say, xi. So I have xi. This is my f of xi. So my f of xi is x cubed minus xi cubed minus xi minus 1. Now f prime of xi, you just differentiate this. So f prime of xi is 3x square I minus 1. So over 3x square I minus 1. So you look for the LCM, 3x squared I minus 1. So you'd have x I in brackets 3x squared I minus 1 minus x cubed minus xi minus 1 equals to xi plus 1. Now, opening the bracket, you'd have 3x cubed I okay, so 3x cubed I minus xi minus into bracket x cubed minus x xi minus xi minus 1 over 3xi squared minus 1. So you open the bracket with minus, you have 3x cubed I minus xi minus x cubed I plus xi plus 1 over 3x squared I minus 1. So then when you simplify, you should have something like, so all this is xi plus 1. So you'll be having something like 2x cubed I. So this cancels this. Yes. Plus 1 over 3x squared I minus 1. So this is our scheme. Then after getting this scheme, we'll start iterating. So let's start. Now, another thing for most of these methods is that you need to get an interval. So for this guy, most times you'll be giving your intervals. But if you're not given, you need to use try and error to figure out your interval. But since I'm solving the same question, don't forget. So, and I already know that one of the answers lie between 1 and 1.5. So I'll be using this interval. So you can pick any of the intervals, either this or this. You still get the same answer. So this is my scheme. Don't forget. Let me highlight it. So this is the scheme I'm going to be using. Now, so let's start our iterative process. So using this, xi plus 1 is this scheme. 2x cubed I plus 1 over 3x squared I minus 1. So now, if I set my I to be 0, this becomes x1 equals to 2x naught x cubed x naught cubed plus 1 over 3x naught squared minus 1. So now, I need my interval. Since I know my interval is between 1 and 1.5, I can pick any one of them to be my x naught. So if I pick my x naught to be, let's say 1.5. So set x naught to be equal to 1.5. So my x1 becomes 2 into bracket 1.5 cube minus or plus 1 over 3 into bracket 1.5 square minus 1. So I have 1.34783. Now, your method of approximation to your approximation, the decimal places you approximate to depends on what you want to get in the final answer. So if I want to get like 4 decimal places, then I should be approximating to like 6 decimal places. So I'll get there quickly. Now, moving on, you do x2. Now, if I pick this same scheme, here's my scheme. Okay, this same scheme. If I set if I becomes 1, so I would have x2, then here becomes x1, here becomes x1. So x2 becomes 2. I'll be using this since this is my x1. 1.34783 cube plus 1 over 3, 1.34783 square minus 1. So I have so my x2 is 1.325200. Now, moving on, x3, I'll replace for x2. So I have 2 into bracket 1.325200 cube plus 1 over 3 into bracket 1.325200 square minus 1. So I have so I have 1.3247. I can rub off this my restrictive skin. 18. Now, if we notice, okay, let me decide to get my answer to like 4 decimal place. If we notice, this thing is I'm having repeated answers in terms of 2 decimal places for these two guys. Here is 1.32, here is 1.32. Now, if I want to get to 4 decimal place, I have to try to get a consistent figure in these 2 decimal places. So I have 52, I have 47. So I will iterate again and again till the figures here are consistent. So moving on, I'll do for x4. So for x4, I would have 2 into bracket, okay, 1.324718 cube plus 1 over 3 into bracket 1.34783 square minus 1. So we do 2. So I'm having 1.3247. Wow, 4717. So if you notice, for this is 3247, this is 3247. Okay, let's do it one more time so that we'll be sure. So for x5, you'd have 2 into bracket 1.32417 cube plus 1 over 3 into bracket 1.324717 minus 1. So I'm having 1.32417. So since for 3 iterations now, I'm having consistent answers. So it means this scheme is converging to this particular answer. So after doing this for 3 times and I am having repeated answers, I can conclude that my question, the answer to my question, to 4 decimal place is 1.32471. Okay, to 4 decimal places 1.3247. So with this, we can say it's converging to 1.3247. And at this point, there's no point iterating again since you just be getting the same answers. So moving on to the next method quickly. So the next method is regular Flasi. So what is regular Flasi method? Let's say I have a curve and I have a line connecting the curve, let's say a chord. Now, if here is A, okay, and let's say here is B, then this place corresponds to, okay, let me use this. So this is B, then this can be f of B, and this is f of A. So regular Flasi method, just the scheme uses the 2-point form in coordinate geometry. So using these 2 points, I know let's call this point A, point B, let's call this point B. So A as A comma f of A as its coordinate, and B as B comma f of B as its coordinate. So if you use the 2-point format to find the gradient, you'll be having something like y. Okay, use the 2-point format to find the equation. You have y minus f of A over x minus f of A equals f of A minus f of B over A minus B. So this is the scheme you have. Now, to get our value, to get the value for x, we have to set f of A to be equal to 0. So once you set f of A to be equal to 0, once you set y to be equal to 0, sorry. So once you set y to be equal to 0, you'd have minus f of A over x minus A equals f of A minus f of B over A minus B. Now, you just work this out and make x subject of the formula. So you have minus f of A in bracket A minus B equals to x minus A f of A minus f of B. So opening the brackets, you have minus A f of A plus B f of A equals x in bracket f of A minus f of B minus A in bracket f of A minus f of B. So moving on, you would have A f of A plus B f of A x into bracket f of A minus f of B minus A f of A plus B f of B plus A f of B, sorry. So this can cancel this. Oh, no. A f of A there. So if you collect like terms, you'd have, okay, this is minus, yes, this can cancel this. So you'd have B f of A minus A f of B when you collect like terms, x into brackets f of A minus f of B. So make x subject of formula, x becomes B f of A minus A f of b over f of a minus f of b. So this is regular false. So let's use this to solve the same question also. Now take note. One thing about this regular falsy is that f of a, one of it must be positive, either f of a or f of b. One of it must be positive or negative. So moving on, you have let's pick our problem. X minus x cubed minus x minus 1 equals to 0. So let's set our, now we need to get if a, okay, now if a is 1 and b is 1.5, then I know that f of a is, so let's look for f of a. That's from our question, that's 1 cube minus 1 minus 1 equals minus 1. So f of b is 1.5 cube minus 1.5 minus 1. That's 0.875. So you have x1 equals b 1.5 f of a minus 1 minus a 1 f of b 0.875 over f of a minus 1 f of b minus 0.875. So this gave me 1.2666. So you have to look for, you have to check if this is positive or negative. So I know that my f of x1 is what? It is negative. So now my a is the negative part. So I would replace this one for a, and I would replace f of a, since f of this is negative, I would replace it for negative. So my x2 becomes, no, I would not be replacing my, I would just be replacing this, my f of this. So I need the value for this. So the value for this is minus 0.23437. So yes, so this is my negative part, minus 1. So I would have 1.5 into bracket minus 0.23437 minus 1 into bracket 0.875 over minus 0.23437 minus 0.875. So So my x2 is 1.1056. 3. So let's check if it's positive or negative. So yes, should have been it. So So I have 1.31591. So when you get your x1, you're going to be replacing both. If the x1 is negative, you're going to be replacing it both for the negative counterpart in regular pulses. So this being x2, so x3. Before x3, I would check f of 1.31591. So that will be answer. So that's negative. That's minus 0.0372, say 25. So moving on, you have x3. So it is also negative. So you'd have 1.5 into brackets minus 0.03725 minus 1.31591 into bracket 0.875 over minus 0.03725 minus 0.875. So we have 1.3234. So you would check again. So it's equal to minus 0.00554.9. So you would replace again. I'll hold this up. So you would have x4 equals 1.5, since it's negative, minus 0.00549 minus 1.3233 in brackets 0.875 over minus 0.00549 minus 0.875. So we're having 1.3245. So you will check again. So f of 1.32453 is giving us 0.000789. So you do some more iterations. So you have x5 equals, okay, this is negative, so you would replace again 1.5 into brackets minus 0.000789 minus, so you're replacing this for this 1.32453 into bracket 0.875 over minus 0.000789 minus 0.875. So x5 equals 1.5 into bracket 0.000789 minus 1.324 into bracket. Oh, mistake somewhere. So I'll do it again. So in brackets minus 0.000789 minus 1.32453 bracket 0.875 minus 0.000789 minus 0.875. Okay, good. So it gave us 1.324688. So we're getting closer and closer to the answers we got before. So we have 1.324 already. So we can go again. Answer cube minus answer minus 1. So it's giving us negative. So f of 1.324688 is also negative. So x6, you'd have 1.5 into brackets. Oh, I can't write negative. We need the values. So you have 0.000127. So we have 0 minus 0.000127 minus 1.32453. Okay, 324688. Sorry. So 0.875 over minus 0.000127 minus 0.875. So in our answer we have 1.5 so 1.324714. So I have 1.3247. So I can do my iteration again. So, but let's check if it's negative or positive and get the value. So f of x6 is actually minus 0.0000162 or 163. And x7, you're going to be replacing 1.5 into bracket minus 0.000163 minus 1 point, you're replacing this for this 324714 into bracket 0.875 over minus 0.000163 minus 0.875. Okay, so we have 1.324717. So if we are picking our answers to say 5 decimal place, the equation, the answer, therefore, our answer is for f of x equals x x cubed minus x minus 1. The answer is x equals 1.3247125 decimal place. So, mhm, okay. So, in the next class, I will be taking finite difference, and I will be recapping on the last method, which is secant method. Thank you.